Alright guys, so we're moving on to projectile motion. Now, before you do all this, hopefully you've had some practice. We've talked about free fall, we've talked about, the parachute lab, but an object falling or being thrown, we're going to call that projectile motion. And it follows some certain traits. So for an object to be in projectile motion, that I'll shorten with PM. So for an object to be in projectile motion, it's only affected by acceleration due to gravity. What I mean by that is essentially when you're throwing something, the moment's out of your hands and the moment right before it hits the ground, we're going to assume that the only thing affecting its speed at that moment in time is essentially gravity and nothing else. No, we're not going to assume it has some sort of way to lift itself up. We're not going to assume that there's even air resistance occurring, even though we know air resistance would be a thing. We're going to simplify it and say it's only accelerating due to gravity. In many cases, air resistance doesn't actually affect it. Only things like a parachute or something that's actually designed to catch a lot of air resistance will not affect it, or if there's very heavy winds. So knowing this is the case, let's talk about how we treat an object that is in projectile motion. So we got this lovely little graphic here, this projectile, and it's going in the shape of what you would expect a projectile to go. A projectile, assuming down is negative, is basically saying, our A of y, which is equal to g, will be negative 9.81 meters per second. As in, as far as I'm concerned, if I'm on flat ground, gravity is going directly down. It's always going straight down. That means, let's say I throw an object up and I let it hit the ground at the same spot. This is the shape of it. It's always some kind of parabola. Now, sometimes, maybe I throw it just straight to the right and it goes just like to the right here. It's the back half. Maybe I'm a little bit higher up and I throw an object up and then it comes back down. Either way, it's some form of this downward parabola. Now, before I even break into these motions, we kind of need to talk about, my initial velocity. So let's say this is my initial velocity. So this is my initial velocity. A neat math trick is dealing with this. So you might recognize whenever you see an arrow, that should be your cue of saying, oh, this looks like a vector. And we know, we've discussed this, that velocity is a vector. And a cool trick, and why we focus so much on vectors in physics, is because vectors have a lot of mathematical properties that make it easy for us. For example, I can split up my v into two parts, a horizontal and a vertical component. And I wouldn't stress too much about why this works, but essentially now any velocities in the x direction and any velocities in the y direction, we will separate them, and that's how we're going to do our math. Now, how is Vx and Vy actually related? Well, it's not Vx plus Vy is equal to V. This won't work, but you might be able to see a shape in there, and that's Vx squared plus Vy squared is equal to V squared. What I mean by this is the shape that we see is a right triangle, and Pythagorean theorem gives us this, this side, both of them squared and added together equals this last side squared, the hypotenuse. So this is kind of what we're basing everything else off of. All right, so let's go back to this object here. When it's traveling this parabola, at this moment, I'll draw with a different color. Maybe this is its initial velocity. And as it goes higher and higher up, it's slowing down, but it's still moving to the right. And eventually, it begins to point downwards the further it goes into its arc. If I were to break this up, and knowing the acceleration is due to gravity, and gravity always goes down, and that's a big key here, is that my acceleration of y is always going down. It's always equal to negative 9.81 meters per second squared. Knowing that acceleration is only going down, that means my a of x is equal to 0 meters per second squared. And so this is the key of why we're breaking it up. And you might think it's we're doing too much work to break it up, but I promise you this is the easier path. Because now my horizontal is constant velocity, and that's the easy one. So let's talk about it. So this object, essentially it's always going to the right. And if I want to draw an object that's going to the right, we'll say we start at 0 meters. And, we're traveling to the right. And so it's a straight line. It's a linear relationship. To draw my VT graph, and I'm going to specify it's my velocity in the x direction. So x is horizontal, y will be vertical. So to draw this, it would be the slope of this. This has one slope, so I have one velocity. Goes for the same amount of time. And my acceleration, my a in the x direction, is just 0. 0 meters per second squared. So this is actually the easy part of projectile motion. We have no acceleration in the x direction. What that means is if I were to break all of these arrows up, what you should notice is that all the horizontal ones are about the same speed or about the same size. But what's going to be changing now is verticality. So now I go to my y direction. Now, what's tricky about the y direction is, we are accelerating. And I know a lot of students have trouble about what is the shape of an object that's accelerating. Is it speeding up? So I have to have an increasing slope. What I'll say is imagine how the throw is. However you throw an object, that's actually the shape of the y position time graph. In this case, because I threw an object, from one starting point and it landed the same height, I'm just going to draw something that looks very similar. Now let's just break down what's happening here. This first half, this object is slowing down in the positive direction and then speeding up in the negative. And that makes sense, hopefully. So you throw an object up, it's slowing down, and then once it comes back down, it's going to speed up again. So that's what this is showing. And this would be a perfect parabola. Now to draw this on my VYT graph, and I'm specifying in the y direction. All right, so let's say this is the red half. So if this is the red half, I'm going to draw it here. An object slowing down in the positive direction, it would look like this. And then the purple half, it speeds back up in the negative direction. This slope here is equal to g, which is negative 9.81 meters per second squared. Now I'm going to do the same thing for my a of yt, and because I have one slope, it's a negative 9.81, that's what I have here for my acceleration. Negative 9.81 meters per second squared. All right, so I have these are my graphs, and roughly all of your graphs should look somewhat like this. And we're going to go through some practice ones. Checking the time real quick. All right, we're good on time. So my x direction is constant velocity, and it's pretty much your x direction is always going to look something similar to this. There should be no curviness going around on the x direction. My y direction is always going to be this curvy direction, but a very specific curvy direction. So your y versus t graph is some part of a downwards parabola. Your VYT is a negative slope, and it's always a specific negative slope, negative 9.81. What's hard with the VYT graph, the hardest part of it is just knowing, where do I start? Do I start in the positive? Do I start at 0? Do I start at negative? If you get that right, you should know exactly how that graph looks. And then the last one is actually easy, your AYT graph, because you always have the same accelerations, negative 9.81. So I'm going to stop the video here, but this is an important one. This whole page here, it seems simple, but this is basing our whole rest of our unit off this.